An object is given an initial velocity of 25 meters per second at an angle of 20 degrees. Solve for the time, twice the time, YH, and R. How high up has the object traveled after 0.4 seconds? How high up was the object at a time of 0.87 seconds? And what happens when you plug in 0 for time? All right, we're going to analyze this problem and look at this in terms of projectile motion. So we always want to go and draw what's actually happening in this situation. You have a path, and you have to launch the object first. When you launch the object, you're going to have an initial velocity, v0. This is going to be launched at some angle theta. It's going to go some distance r, which is the range. At half the time, it's going to be at that point. That point, we have an xy value, an x coordinate and a y coordinate, and that's r over 2 and y sub h. R over 2 is half the range. Y sub h is the maximum height that it's going to attain. The velocity at that maximum height, we're going to call it VYF. That's equal to 0 meters per second. Because as the object is launched upward with some initial velocity, it's going to travel upward. Gravity's going to act on it and slow it down. As gravity slows it down, it's going to have a final velocity at this point equal to 0. Now, V0 is equal to 25 meters per second. The angle theta at which it's launched is equal to 20 degrees. We don't know how much time it's going to take to get to that point. I'm going to go ahead and write the last couple of things that we do to analyze the drawing. That's 90-degree angle. This is Vx0. That's the velocity of the object in the x component direction only. And this is Vy0. That's the velocity of the y component direction only. So it's the velocity of the object traveling upward. Now remember from earlier, an object in the x direction travels at a constant speed. An object in the y direction is slowing down until it gets to 0, speeding up as it falls down and hits the maximum range point. All right, now let's solve for the time t. T is equal to V0 sine theta divided by g. Time is equal to 25 sine 20 divided by 9.81. If we punch this in our calculators, we're going to get a time of 0.8716 seconds. Now, normally I would just round that off to 0.87 seconds, and even sometimes 0.9 seconds, and I wouldn't care. But for this problem, I'm going to keep it out to 4 decimal places for a specific reason. You're going to understand that reason as we go along. Now, that's the time of 0.8716 seconds. That's how much time it's going to take to get to this point. All right, now we're going to do this. Twice the time is 2 times 0.8716. Twice the time is the time that it's going to take to get to this point, the maximum range. Twice the time is going to be 1.74 seconds. Now we're going to solve for y sub h. Y sub h is equal to V0 squared sine squared theta divided by 2g. Y sub h is going to be equal to 25 squared sine squared of 20 divided by 2 times 9.81. If you plug this in your calculator, you're going to get a value of 3.73 meters. This means that the object, in a time of 0.8716 seconds, is going to reach a maximum height of 3.73 meters. All right, now let's solve for the range. The range is how far it's going to go over in the x direction. The range is equal to V0 squared sine 2 theta divided by g. And that's going to be 25 squared sine of 2 times 20 divided by 9.81. And if you plug this in, you're going to get a value of 40.95. Now, be careful of this, plugging this in. This is 2 times 20, so that's a sine of 40. And this over here, what you need to do to plug this in your calculator is sine of 20 squared, or sine of 20 times the sine of 20. So 2 different ways to plug this in your calculator to get sine squared of 20. All right, now, the next part of the problem asks for where is the object going to be at a time of 0.4 seconds, t equals 0.4. Now, if we look back at the time over here, this time is 0.8716 seconds. That's to get to this point. A time of 0.4 seconds is going to be somewhere along this path. But the great thing about these equations over here, these equations are able to solve for any point along the path at all, for any time. These equations were derived as manipulations of the linear equations specific to the y direction with an initial velocity at some angle. So these equations take into account Vx and Vy. All right, so we're going to use those equations. First, we're going to look at where the object, in order to find out where the object is located, you could figure out which of those equations to solve directly, and that would be the third equation. You could get the distance. But if you didn't initially know where to start, and you chose any one of the equations, you might solve for the velocity first. So Vyf is going to be equal to V naught sine theta minus gt. And you could start at any of the equations and plug in the final velocity into one of the others. So we're going to actually first solve for the final velocity at a time of 0.4 seconds. But we won't know exactly what position or height the object will be located. So Vyf is going to be equal to 25 sine of 20 minus 9.81 times a time of 0.4 seconds. If you plug this in, you're going to get a value of 4.626 meters per second. All right, that's the final velocity at that time. Now we're going to solve for the distance, how high up, and that's Yf minus Yi. We can use any of the other equations at this point. We'll just go ahead and choose 1/2 Vyf, because we just solved for Vyf, plus V naught sine theta times time. And we know all the values except for the distance. So distance equals 1/2. Vyf is 4.626 plus V naught is 25 sine 20 and a time of 0.4. So the distance up along the y-axis is going to be 2.635 meters. And let's do a quick check. Now, the maximum y value at a time of 0.87 seconds is 3.73. So the distance that we calculate for a time of less than this should be a distance that's less than this. So we go over here, our time is 0.4, it's less than 0.87, so we should get a distance less than 3.73, and we do. We get 2.635. Alright, now let's do something a little different. Now let's check it for a time that's less than 0.8716, but close to it, to see what the distance would be then. We're going to erase this part, but leave the rest. And we're going to choose a time equal to 0.87 seconds. Now, doing this, the reason that you choose values close to known values is to, 1, check to make certain that you understand how to solve the problems, and 2, check to make certain that your derivations of the equations are correct. So you know that if you derive the equations and you made a mistake, you can check it by plugging in random values that are close to known values. So a time of 0.87 seconds. We're going to do the final velocity equation is equal to V naught sine theta minus gt. So Vyf is going to be equal to 25 sine of 20 minus 9.81 times a time of 0.87. Vyf is now equal to 0.0158 meters per second. And that makes a lot of sense, because the final velocity at the top of the path right here is 0 meters per second. But that's at a time of 0.8716 seconds. We just solved for a time of 0.87 seconds, which is almost 0.8716. And we get a velocity that is almost equal to 0. That final velocity is 0.0158 meters per second. That means that it's slowing down and coming to a stop at the top of the path. All right, now, what is that y value? How high up did it go? We know that we should get something slightly less than 3.73. So the distance is equal to yf minus yi is equal to 1/2 vyf plus v naught sine theta times time. Yf minus yi, that's a change in height, which is just the distance, 1/2. Vyf here is 0.0158 plus v naught is still 25 times the sine of 20 times a time of 0.87 seconds. And you get a y value, a yf minus yi. The y value is going to be equal to 3.726 meters. And now you know why I kept all these decimal places. Normally I just round them off and say that's perfectly fine. And when you take a quiz or a test, you can round them and that's fine. But here I'm checking to make certain that the equations, the derivations are correct, and that your answers make sense. So this is what you should be looking for. You get, at a time of 0.87 seconds, a value of 3.726, which is a little bit less than 3.73. So your answer makes sense. Let's do one final check. And this is a simple check. What would happen, or what should happen, at a time of 0? If your time is equal to 0, the object shouldn't have attained any height at all. So if you go to yf minus yi equals, let's just do v naught sine theta t minus 1/2 gt squared. And if you plug in a 0 for time, that zeroes this out, and that zeroes this out, which means that your yf minus y value is equal to 0, and at a time of 0 you haven't gone anywhere. So your final check is with a time of 0, and your equations still check out.